In the previous video, we saw the main defining idea of trigonometry, which is that the sine and cosine functions give you the y and x coordinates respectively of a point on the circle determined by rotating around by a given angle. So now let's put some more flesh on that idea by computing some specific values of those functions. So here I've repeated kind of the x and y axes with a circle of radius 1, which I've not actually labeled, but it is radius 1. So let's kind of put more values in that table. So I'll go to this notation which was introduced in the last video of using the Greek letter theta to represent an angle. And I'm still going to write these angles in degrees for the time being, but shortly, perhaps in the next video or the one after, we'll see that there's a much more natural way to measure angles besides degrees. So I'll write these in the xy order. So we'll make a table of theta, and then the x value, which is cosine theta, and the y value, which is sine of theta. Okay, so for instance, we saw in the previous video, and I'll redraw this triangle here, but we saw that if you have a 45, 45, 90, that's a bad triangle. Let me draw again. We have a 45, 45, 90 triangle, so these two angles are supposed to be equal, top and bottom, with hypotenuse 1, that these two have the same lengths. So the two legs, the x and the y coordinates, both have length 1 over root 2. So that gave us one value. So we know how to evaluate the sine and cosine of 45 degrees. They're both 1 over root 2. And now we're going to repeat for a 30, 60, 90 triangle, which is likely the only other triangle for which you have the values memorized. So we remember that a usual 30, 60, 90 triangle, which let me just draw another copy down here. So this is the 30, and the other one is the 60. So remember that the legs of that triangle come in the ratio 1 root 3 and 2, right? So the hypotenuse has length 2, or in general 2x. It can be twice anything. So 1 goes here, and then the root 3 goes here. So this is the usual ratio between the lengths for a 30, 60, 90. And you can check that this satisfies Pythagoras, because root 3x quantity squared gives us 3x squared, and add that to 1x squared gives us 4x squared, which is indeed equal to 2x quantity squared. So this satisfies Pythagoras just as this satisfies Pythagoras. Everything is copacetic. So now we need to find what are the two lengths of the legs of our 30, 60, 90 triangle up here. And now we just need to find what value of x makes this triangle the same as this similar triangle. So here the hypotenuse has length 2x. We want to match that to a hypotenuse which has length 1, which means we need x equals 1/2. Here I've done a bad thing by using x in two different ways, x for this axis here and x for the unknown scale in this triangle, but I trust that you can make sense of that. So if we set x equal to 1/2, then we have a triangle whose hypotenuse has length 1, which is good. We see that this vertical piece is going to have length 1/2. And the horizontal piece, which gives us the x coordinate, is going to have length square root of 3 divided by 2. Good. So now we've figured out the sine and cosine of 30 degrees. So for 30 degrees, we have that the x coordinate we've just found is root 3 over 2, and the y coordinate is 1/2. But the nice thing is that we actually get a second point evaluated for free, because if we go to 60 degrees, which is up here, so a 60-degree triangle, we see that that has the same side lengths as the other triangle, because both triangles have a right angle, a 30-degree angle, and a 60-degree angle. It's just that the x and y are reversed, right? So you can imagine taking this triangle and simply rotating it so the 60-degree angle is now here and the 30-degree angle is now here, and all that does is switches the two values of 1/2 and square root 3 over 2. And if you don't believe me, then you can work it out as an exercise. But the upshot is that now we know cosine of 60 degrees and the sine of 60 degrees as well. Good. So Now we have some concrete values of sines and cosines. Of course, sine or cosine of, say, 0 degrees, 90 degrees, 180 degrees, you can evaluate very easily because they're going to be 0, 1, or minus 1 appropriately. So these will be kind of the important values to keep in mind. These are not things that you should have to work out when they appear in a problem. These are one of the few things that you should have memorized so you can use them immediately when they appear in a problem. Good. Okay, so that ends the second video. I will do one more video where we kind of prove a result, so a first actual problem in trigonometry rather than an exercise.